All right, so questions. Five 5.3, like what? No, I mean, tell me what the problem is. All right, prove if A times C divides.
B times C, then A divides B.
So what does it mean to say A times C divides B times C? That might be an interpretation of it, but that's not what divisibility says. So what does it mean when we say X divides Y? Remember the definition? That wasn't the definition we originally used when we said divisibility, though. Say again? Y cross X. Y equals X. Not necessarily. Y equals X times K. And what is K? And K is an integer. So that's our one and only true definition of divisibility. When we say X divides Y, that means Y can be written as X times some K, where K is an integer. Okay, and from that definition, we can try to do other things like this question. So if AC divides BC, what does that mean in terms of this definition? So given AC divides BC, what can we say? Close. Yeah. BC equals AC times K, where K is an integer. And then divide both sides by C, because we're told C is not 0, right? So B is equal to A times K, which is only legal because we're told C is not equal to 0. So now we've shown that B is equal to A times K. And what can we conclude from that using this same definition? You can't conclude A equals B times K just because B equals A times K, because then B would be equal to like A times B times K squared or something. But this is the definition of A divides B. Because saying A divides B means B equals A times some integer. And we've just shown B equals A times some integer, so we can say A divides B.
Could you divide C out from the very beginning, since it is on both sides?
We don't have a rule for that, but that's basically what we're showing. But up here, AC divides BC, we don't have a rule that says we can divide both sides by C. We do now, though, right? But without knowing that this is true, that this implies that, you're not allowed to just cancel just because there's a C on both sides.
So is it kind of, I mean, the way I'm looking at it now, since it's not an equal sign, you can't just get rid of the C.
Right, right.
But is it kind of like distribution, where you can kind of like multiply the whole A divides B times C and then put it in?
Sort of, yeah. I mean, that's what's going on underneath here, basically, is we're doing a distribution or a cancellation. But one of the things that's tricky about this subject is that we're used to things where we have a c on both sides, we can just cross out the c. But that's not always going to be the case in general. In this case, it happens to be, but there's other things we might do where that doesn't work. So that's why we want to be able to go back and sort of prove that that cancellation works. Does that make sense?
Yeah, I guess I'm just getting hung up on definitions.
Yeah, that's
Kind of really hard.
sure. I mean, that's the point of these is to stress the definitions, because that's really the only thing we have to work with. But right, box divides triangle means triangle equals something times box, where that something is an integer. Try to think of it like that, right? Get away from the variables, get away from the numbers. Blah divides what's it means that what's it is a multiple of blah, right? And this square, this triangle can be anything. They could be numbers, they could be variables, they could be equations. It makes no difference. This is the definition of this divide symbol. So now if we just make this AC and this BC, then this is BC, this is AC. That's how we got to this. BC equals K times AC, right? But sometimes it helps to kind of like step way back and force yourself to not think of this as regular algebraic equations. Just think of it as, I mean, this is what a definition is. It's the same thing when we talk about P of n, right? Sometimes it's useful to think of P of, you know, whatever says. And then if we want to find P of n plus 1, we just substitute an n plus 1 for the triangle. But yeah, this kind of proof is challenging because in some sense it's too simple, right? It goes against our belief of what a proof should look like. But it's not simple at all until you sort of like get through that layer, and then it's really just kind of like plugging in the place. But knowing how to do that so that it actually gets you where you're going, that's the thing that practice brings. All right, other questions? Yeah.
For some of the other proofs in this section, we use
If it's valid, sure. I don't know what the questions are off the top of my head, but if you have a particular one you think might work with induction, we can talk about it.
I was specifically thinking about the square of an odd integer minus 1 is divisible by 4.
Square of an odd integer minus 1 is divisible by 4. So is it something like this? Something like that. I believe you can do this by induction, but I'd like you to try to do it using modular arithmetic. I believe you can do a valid inductive proof on this, but the purpose of this question is to think about things in terms of modular arithmetic. So try doing it like that. And when we're saying divisibility by 4, that's a hint that you want to work mod 4. And remember, the idea of modular arithmetic is we can take all the integers and we can reduce them to just 4 integers, 0, 1, 2, and 3. Because everything's congruent to either 0, 1, 2, or 3. So if we can show that this is true when n is congruent to 0 mod 4, when it's congruent to 1, when it's congruent to 2, when it's congruent to 3, we'll be done. And in fact, since n is an odd integer, we know it's never going to be congruent to 0 mod 4, because it would have to be even. And it can never be congruent to 2 mod 4, because it would have to be even. So every number in the world, every odd integer, is either congruent to 1 or congruent to 3. And if you can prove that this statement is true for any number congruent to 1 or congruent to 3, then you're done. So try attacking it that way and see where it gets. And it's a general model for a lot of different things we can show. Others? All right, so let's continue talking about primes. So we talked about an infinite number of primes, right? And we talked about Mersenne primes. And we talked a little bit about density of primes. So if we were to make a graph where we have n along the x-axis and the number of primes less than or equal to n on the y-axis, what kind of shape might we expect this graph to have? How many primes are there less than or equal to some number n? And yeah, it feels like it might be kind of logarithmic. I mean, it's probably not going to be linear, because I would say that from 1 to 1,000, there's a certain number of primes. From 1 to 2,000, there's twice as many. From 1 to 10,000, there's 10 times as many. And if you look at primes, they tend to get spread out more and more. So we don't really expect something linear. And if it looked like this, what would that mean? If it flattened out at some point, logically, how could we interpret that? Say again? Number of primes are the same. In other words, there's a limit to how many primes there are. If there were only a finite number of primes, then at some point when we got to some number n, no matter how much further we looked, we'd never see any more primes, right? So that would imply a finite number, and we don't expect that. So we expect this thing to keep growing. But in fact, it looks something like this. Right? It grows, but it starts off growing pretty quickly, and then it starts to level out. And it never gets completely level, but it grows less frequently as n gets larger. So there's a theorem about the nature of this. And this is called the prime number theorem. So let's make a function. So let P of n be the number of primes less than or equal to n. So here's the prime number theorem. As n gets bigger and bigger, so we can say limit as n goes to infinity, the limit of the number of primes less than or equal to n divided by the natural log of n is 1. So roughly speaking, for large n, the number of primes up to n is the natural log of n. And remember, natural logs are logarithms, base e. So there's a quirky relationship between divisibility of integers and this magic number e that pops up all over mathematics. And there's a ton of proofs for this, and these proofs come out of various fields of mathematics. And to me, that's just a really bizarre result, because the logarithm based this weird number e, 2.71828, tied into the number of primes up to n. It's got no business being there, but it is. And it's just one of those ways in which natural logs and the number e itself just pops up everywhere in mathematics and nature and so on and so forth. So what is e? It's got that value, but what is it? Has something to do with exponential growth.
The number where if you raise it to x, its derivative is the value.
There you go. This is probably the reason why e pops up everywhere. It's a function that represents its own rate of growth. So x squared, its rate of growth is 2x. And square root of x, its rate of growth is whatever that is. And sine of x, its rate of growth is cosine of x. But e to the x is the function whose rate of growth is e to the x. It describes its own rate of growth. So if you have some process where something, the population of a bacteria colony, is described by e to the t, where t is time, at any point in time, the size of that population tells you how quickly the population is growing, which is kind of what you expect with natural processes, because the larger the population, the faster the growth, because there's more reproduction going on. So it ties into natural processes very nicely, but it also gives us, you know, all these weird things like this, and the weirdest of all, that one which we mentioned before. And so on and so forth. Well, so primes tend to spread out. If you look between 1 trillion and 2 trillion, you're going to find fewer primes than if you look between 0 and 1 trillion, right? And you're going to find even fewer primes if you look between 9 trillion and 10 trillion, right? So each of these regions has a trillion integers in it, but the number of primes in there gets smaller and smaller and smaller. Nonetheless, we keep finding primes like this, so-called twin primes. We can't have two consecutive integers that are prime in general, because two consecutive integers, one of those is going to be even, and the only even prime is 2. But there's no reason we can't have two consecutive odd numbers that are prime. And when we have that, we call those twin primes. They're as close to each other as reasonably possible. And we find twin primes no matter how far out we look. They get rarer, but between 9 trillion and 10 trillion, we'll still find some primes that differ only by 2. But it's a bit of an unknown question about whether or not twin primes always exist, or if there's some point beyond which all primes are separated by at least 4. We don't know the answer to that. It certainly seems less likely to find twin primes as your numbers get larger and larger and larger, but do they ever completely disappear? Don't know. It's an open question. And it's another one of those questions that's pretty easy to formulate, but surprisingly difficult to actually prove. So that's one open question related to primes, is the existence of twin primes. Bless you. So what are all the factors of 6 other than 6? Positive factors. 3, let's count 1 also. And we don't count 6, though. So we're just looking for factors less than the number. So for 6, the factors are 1, 2, and 3. What's 1 plus 2 plus 3? All right, what are the factors of 28? 1, 2, 4, 7, 14. So 14, 7 is 21, 25, 27, 28. This doesn't happen very often. Prime numbers, it never happens, because prime number is the only factor less than the number is 1. So in those cases, the sum of the factors is certainly less than n. Powers of 2, the sum of the factors is always 1 less than the number itself, because the only factors of a power of 2 are all the smaller powers of 2. And in some cases, you can find numbers where the sum of the factors is bigger than the number. But this particular case where the sum of the factors is equal to the number, that's what we call a perfect number. And perfect numbers are pretty interesting. For one thing, they're related to Mersenne primes. So here's a formula. If 2 to the p minus 1 is a Mersenne prime, then 2 to the quantity p minus 1 times that Mersenne prime is a perfect number. So 2 cubed minus 1 is prime, so 2 cubed minus 1 times 2 squared, that's 7 times 4 is 28. 2 to the second minus 1 is prime, so 2 to the second minus 1 times 2 to the first, that's 3 times 2 is 6. That's a perfect number. 2 to the seventh minus 1 is prime. So 2 to the sixth times 2 to the seventh minus 1 is perfect. So that's 64 times 127. And it turns out that all of these perfect numbers will be even because 2 to the p minus 1 is going to be even. It's a power of 2. But an open question is, are there any odd perfect numbers? And we don't have a final answer to that. But a lot of progress has been made on it. You can look online, Google this, and you can see that we know there's no odd perfect numbers below some ridiculously huge number, and that if there is an odd perfect number, it has to have all these bizarre characteristics, which makes it very unlikely to exist. But nobody's been able to prove that there are no odd perfect numbers. It's a simple question to state: is there an odd number that's equal to the sum of its factors less than the number? But it's unknown whether that's true or false. All right, so this brings us to PA2, which is Goldbach's conjecture. So Goldbach's conjecture basically says that every even number can be written as the sum of 2 primes. We can't write 2 because 2 would be 1 plus 1 and 1 is not prime. But 4 is equal to 2 plus 2, and those are both prime. 6 is equal to 3 plus 3. 8 is equal to 3 plus 5. 10 is equal to 5 plus 5. 12 is 5 plus 7. 14 is 7 plus 7, but it's also 3 plus 11. 16 is 3 plus 13, but it's also 5 plus 11, and so on and so forth. So, I mean, it certainly seems reasonable with the first few even numbers. And in fact, you can try this for larger even numbers, and it's pretty easy to find 2 primes that add up to the number, but nobody's proven that this is always the case. It's an open problem. And again, we've shown that if there's an even number that can't be written as a sum of 2 primes, it's got to have all these characteristics, and it's got to be bigger than this ridiculously big number, and so on. But nobody's found a general proof that Goldbach's conjecture is true, or a counterexample to show it's false. Counterexample is easy. All you got to do is find one even number that you can't write like this. And if you pick that even number, you just have to subtract all the primes less than that number and show that the difference is never a prime. If you do that, then you know that violates Goldbach's conjecture, and you got fame and fortune, or at least bragging rights. But it's an open question. So your programming assignment, number 2, is to explore this. So here's what you're going to do. You're going to write a program in C or C++, and your program is going to ask you to enter an even integer. And it's going to ask you to enter the number of integers you want to test. So I might say, okay, I want to start at 100, and I want to test 1,000 integers. And it should go ahead, and it should take every even number, starting with your starting point, and try to write it as a sum of 2 primes. So produce a table that says, 100 equals 97 plus 3, 102 equals 97 plus 5, and so on, 1,000 times, or however many times the user asks you to do this. So whatever their second number is. So take the first number, write it as a sum of 2 primes, go on to the next even integer, write that as a sum, and keep going. If you find an integer that you cannot express as a sum of 2 primes, right, print it out like 1,000,000 times and email it to yourself and stuff like that, because you've just made history. So your program's written in C or C++, and what I want you to turn in is a copy of the source code of your program. You got to show me the source code, and a copy of the output of the program, which you ask to generate 100 sums starting with 1,000,000. So run your program, say I want to start with 1,000,000, and I want to see the next 100 even integers. Take all of that, copy it, paste it into a document, save it as a PDF, upload that PDF. Okay, I don't want a screenshot. I want you to do this on a window, Linux, something. Grab the text, paste it into a document as text, and then export it as a PDF, upload the PDF. So the PDF, one file will contain the source code for your program, and then 100 lines of output, which will show 100 even integers starting with 1,000,000 written as a sum of 2 primes each. Is that clear? Okay, so how do you do this? Well, write yourself a function that tests to see whether a number is prime. Don't use a built-in library function. I want you to write the prime test yourself. And how do you test if something's prime? Just divide it by all the numbers between 2 and the number square root, okay, including the square root. For 1,000,000, as we said the other day, this will make a big difference in efficiency. If you go up halfway, you're going to have to do 250,000 divisions. If you go up to the square root, you only have to do 500 divisions. So it'll run a lot quicker doing that. And you can use the modulus operator if you want instead of dividing, and just see if your number modulo the possible factor is equal to 0 or not. Okay, this third point is critical to performance. There's 2 ways to approach this question. So let's say we want to know if 10,000 can be written as a sum of 2 primes. Here's what you do not want to do. Okay, don't do this. Generate your first prime is 3. Generate your second prime is 3. Add those together, see if you get 10,000. No. Okay, take your first prime, add your second prime, see if you get 10,000. No. Take your first prime, add your third prime, see if you get 10,000. No. When you get to the end of that, move on to your outer loop, take your second prime plus your first prime. Don't do that. Okay, it will not finish. I've had people do this, they leave it running for 5 days, it does not finish. Okay, this is the most inefficient way that you can reasonably do this problem. It makes logical sense, right? Generate all the primes, put an outer loop, generate all the primes, see which ones add up, and look for something that adds to your number. But it's going to be really inefficient. So here's an easier and better way to do this. So we want to know if this is the sum of two primes. So a single loop that goes through all the prime numbers up to 10,000. Subtract the first prime. See if the difference is prime. If it is, you're done. If not, subtract the second prime. See if the difference is prime. If it is, you're done. If not, subtract the third prime and see if the difference is prime. And keep going until you either run out of primes to subtract or you find something where the difference is prime. As soon as you find that, let's say that 9993 is prime. Well, it's not. Let's say this one is prime. Then you can write out 9989 plus 11. And chances are, in most cases, you'll have to do maybe 5 or 6 subtractions at the most before you find a difference that's prime. Okay, and that's going to be much more efficient than looking at sums of primes. So if you've coded this up and it's taking like 5 hours before it like finds one number, take a look at this again or ask questions, because it's probably not being done in a very efficient way. Okay, so that's what this spells out down here. Calculate the first prime x, test x minus 3. If it's not prime, calculate the second prime 5, test x minus 5, and so on. All right, so that's PA2. It's due, I think, March 9th. Come on, you can do it. There we go, March 9th. All right, so you got plenty of time. But don't leave it until the 8th, please. Do what?
Leave stuff running on the server. Extended amount of time.
You can, as long as it's not like really grinding the CPU, but it's got a few cores. This should not take more than like a couple of seconds at the most to run. I can, yeah. And you can kill your own by Control-C, or if it's in the background, you can do a kill-9 and kill it off. You don't have to do this on the server. You can do it on your own machine if you like. You can do it on a Raspberry Pi. All right, questions on that? All right, so let's talk about greatest common factor. And this is something called the Euclidean algorithm. So here's the idea. You have two numbers. We know that we can factor those numbers into primes. In some cases, there may be a prime or multiple primes that divide both numbers. And we want to be able to find what the largest integer is that divides a pair of numbers. We do this in school when we're taking fractions and trying to simplify them. We find the greatest common factor and we divide it out from the numerator and denominator. So, for example, this is sometimes called greatest common divisor, GCD. So the greatest common factor of 25 and 15 is 5. 5 divides both of those numbers, and there's nothing bigger than 5 that divides both. Greatest common factor of 30 and 15 is 15, because that divides both numbers, leaving you with an integer. Greatest common factor of 31 and 15 is 1, because there's nothing bigger than 1 that divides both of those. Why is that? Because 31 is prime. In general, the greatest common factor of a prime and some number n is going to be 1, as long as n is less than p. I could do 31 and 310, and the greatest common factor would be 31, right? But if this is prime and this is something that's smaller than p, we know that nothing smaller than p divides p, so the GCF is going to be 1. So we'd like a way to be able to find the greatest common divisor systematically. And that's what the Euclidean algorithm is for us. So let's just work through this. Let's just find the greatest common factor of 735 and 252. I don't know what it is off the top of my head. One of them's even, one of them's not. So here's how this algorithm works. So take your larger number and write it as something times your smaller number plus some remainder. So 252, it's not going to go into this 3 times, because that would be 756. But it will go in twice. So 735 and twice 252 will be 504. So the remainder is going to be 231. Okay, we don't care about the 2. That's just the number of times that our second number went into our first. What we care about is that second number and the remainder. So after you've written this, your first number is something times your second number plus a remainder. Copy that over here. And copy the 231 over here. In other words, repeat the process. Try to write 252 as something times 231 plus some remainder. So 231 will go into 252 once, and the remainder will be 31, 51, 21. All right, same thing. Copy this over here. Copy this over here, and write 231 equals something times 21 plus something. So how many times can 21 go into 231? I think it's going to be 11. And it goes in exactly 11 times. So 11 times 21 plus 0. Once you get down to this point where you have a remainder of 0, this is your GCD. All right, so let's try this a few times. So someone pick a number. 241? All right, someone pick another number. 1,337. So, oh, you can trust us. So let's find the greatest common factor of these two numbers. So we want 1337 equals something times 241 plus something. So I'm going to cheat and use a calculator. Maybe. So 1337 over 241. So this goes in 5 times. And if I subtract that off, I get a remainder of 132. So now you want to write 241 is something times 132 plus something. So 132 twice would be 264. That's too big, so it's going to be 1 times 132. And let's just do 241 minus 132 is 109. And so 132, let me put my little arrows in here. 132 equals 1 times 109 plus 33. 109 equals, looks like 3 times 33 is 99. Did I mess up? This here. Yeah. Good, thank you. All right, so 109 equals something times 23 plus something. So I think this is 4, which is 92. Plus 17. 23 equals 1 times 17 plus 6. 17 equals 2 times 6 plus 5. 6 equals 1 times 5 plus 1. And 5 equals 5 times 1 plus 0. And once we get down to a 0, this is our GCD. So after all that, this and this have no common factors other than 1. Which is a special case that we say these two numbers are relatively prime. So two numbers are relatively prime if they have no common factors. So another way to do this is to actually factor these numbers and look for things that they have in common. So in this other case where we were working with 735 and 252, well, let's do some quick factoring. So 735 is 5 times 147. Uh, 147 is 3 times 49, so it's 5 times 3 times 7 times 7. Gives us 735, and 252 is 2 times 2 times 3 times 3 times 7. And so if we want to find common factors between these, it looks like we're going to have a 7 in common, and we're going to have a 3 in common, and nothing else. And 7 times 3 is our 21. All right, so 60 seconds. Why does this work? It's modular arithmetic again. If we have something which divides this number and divides this number, it's also going to divide this number. So 735 equals something times 252 plus 231. That means 231 equals 735 minus 2 times 252. If this number is divisible by x and this number is divisible by x, we've already seen that this number is divisible by x and the difference is divisible by x, which is this. So when we're writing out our numbers like this, we're looking for a common factor to this number and this number. If there is such a factor, it's also going to be a factor of this number, right? And of course this number, because that's one of the numbers we're looking for a factor of. And if we have a factor of these two numbers, it will also be a factor of this. And since it's a factor of this and this, it'll be a factor of this. But the way that we're doing this, these numbers that we're getting are always getting smaller, and eventually they're going to get so small that they're either equal to 1 or 0. Right? So when they come down to 0, whatever the last number was, that's a common factor of both numbers. So this works basically because we have this property that when we have something that divides two numbers, it divides their difference also. All right, so there's a homework question that has a bunch of pairs of numbers for you to find the GCD of. That's the algorithm that you want to use, Euclidean algorithm. All right, we'll continue from there tomorrow. We will look at some applications of all of this stuff.